This is an informal presentation of a system called Coda-X that was programmed on the Xerox Lisp machine and 1186 models. This was done about 10 years ago, 1986 to 88, I would say. And it's entirely programmed in Inter-Lisp-D, a language that has since disappeared, and this model of machines also have disappeared. And it's not clear that this program will ever be ported on another platform, so I take this chance while we still have one machine working to present a little bit what this work was all about. Basically, what is in there is an adaptation of a parser, a deterministic parser done at Bell Labs by Don Hindle that I translated and adapted for this machine, to which I added lots of different functions, and a semantic interpreter built on top of the parser. There are two versions of that interpreter. One is hard-coded in Lisp. It actually takes the output of the parser and creates semantic representation. The second version, which was never entirely completed, is basically a rule-based graphic programming language in which a non-programmer but a language engineer could express rules to convert syntactic representation into semantic forms. First, let's have a look at the parser. I will start by typing a very simple example. Let's try I am parsing an easy sentence. I hit the return key, then I get a trace of the application of rules, and I get a tree up there. Let's have a look at it. It's a sentence with a noun phrase with a pronoun I, and then an auxiliary made out of tense and verb present tense, then a verb phrase with the verb ing, a noun phrase which is made out of a determiner, and a noun phrase with an adjective and a noun. Looks pretty good. So let's try something maybe a little bit more difficult. Okay. What about there are different kinds of parsers for different kinds of needs. Still, we get a trace of the application of rules. Then we get a bigger tree. Let's zoom a little bit on that tree, see what we have up there. We have a sentence, a noun phrase, auxiliary again, a verb phrase, present verb, then a noun phrase, different kind, it's okay, a PP of parsers. The words that are in boxes, it's because they're not known by the parsers, but it can guess the part of speech of unknown words. And then there's a PP at the end for different kinds of need. The prepositional phrase of need was correctly attached to the noun phrase, but the other one, for different kind of needs, there's a symbol on top of the PP which indicates that the parser could not attach it anywhere. Because the parser has a variety of problems, some fixes that I made were done to correct the output of the parser rather than actually change the way it operates. A few modifications were made in the parser itself, but most of them were made to fix after the fact, looking at the tree and at the sentence and the word that made up the sentence, a few fixes for structures that create some difficulty. Here, there are problems with conjunction, with adverbs, with adverb phrase, with passives, compound nouns. In that case, we have a PP. We can fix it automatically, in which case it's going to do minimal attachment. but we could prefer an attachment to the VP or to the NP. In that case, why don't we try attachment to the VP? So in that case, the PP was attached to the verb be here. Yeah, and that, as you might have noticed, the parser is extremely fast, and that's probably the biggest quality of deterministic parsers. This particular one was obtained from Bell Labs in New Jersey, and it was delivered on a tape from a VAX machine. So it was loaded on a VAX machine at McGill, then it was downloaded onto a Mac. Then I had to build a special cable to link Mac to a Xerox machine through a serial port. Then it was transferred to the Xerox machine, then painfully translated into Interlisp D, which is a very different Lisp than Franz Lisp. Originally, the parser could only print trees on the text form. So one thing I did is to create graphical trees which can directly be edited, as I'm going to show you soon. Trees can be edited in two different ways. In one case, we can simply see a Lisp version of the tree, in which nodes can be removed or altered or added. There's also a possibility to edit the tree directly on the graphic representation. For instance, we could just move nodes physically there, or add some nodes, add a label, for instance, test, and then move it around, then add a link, etc., delete a link, change a label, etc. The reason why this was needed is those trees are going to be used as the input for a semantic parser, and of course we need to have a way to fix the parse when it's incorrect. So there are basically two stages. There are those fixes that I've shown you that can be used to attach PPs and do fix some problem with conjunctions and other things, and we can directly edit the trees to get the result. Also, because deterministic parsers are extremely complex to understand, the rules are very tricky, are not natural at all, I built a fairly powerful trace of the application of rules, and eventually this trace shown to be useful in explaining to linguists who are interested in the subjects the way a deterministic parser works. For instance, if I reparse the sentence we last parsed, then we now see two things in the parse window. In the first part, we see the exact state of the parser before the application of the first rule. For instance, we see the current node is nil. There are three windows corresponding to the first, in that case, the first three words in a sentence. There, which can be a noun phrase or a propositional phrase. Be, which is a verb present. Different, which is an adjective. And then there's the node stack of all nodes there. In another window, we can see the exact rules that's going to be applied. The rule is called their operators. The rule basically reads like that. If in the first window there is something that can either be a noun or a preposition, and in the window 2 you have something that is part of a category called aux edge, you do the following action. You uncat the first window and call it PP. So it's just a disambiguation rule. So if I click on the continue button, we see the result. In window 1 we now have NP. So the second rule is going to be tense in 2. If you have an NP in window 1 and a V tenseable in window 2, that you insert quote tense quote star. Let's see what it looks like. So a new node tense was inserted at window 2. If I just go a little bit fast in the trace, we see step by step how the resulting parse tree is actually built. that particular rule, the whole sentence build so far was pushed towards the end of the node stack to do some work on the combination of adjective and noun, and eventually this is going to be added to the sentence. Now a noun phrase is built. The prepositional phrase that goes with kind is built. And we see that the other constituents have been stacked and waiting for this group of rules to finish their work. Etc. Also, a lexicon editor was added. For instance, if I select word like different here, I can see the lexical entry. We could add syntactic markers and semantic markers, which are used by the semantic form generator. We can add a different form of adjectival complements. The syntactic marking is fairly simple and basic in that parser. For instance, this word, the word parser here, was not in the dictionary, so we could add it. For instance, the part of speech. We have a variety of possibility. In that case, we'll decide it's a noun. But then it could be an ambiguous noun, so we have a bunch of possibilities, like it could be a noun or an adverb, a noun, an adjective for a verb, etc. The purpose of FIDIC, this parser, was to analyze transcription of free speech. So it's extremely robust, and it has a surprising coverage, even for a small vocabulary of around 3,000 to 5,000 words. It is extremely fast. At the time it was done, this was probably the fastest and most accurate English parser in the world. It might still be today. I know that some work have been done with FIDIC after this translation was made, so there's probably a version right now that's even better. The biggest problem with deterministic parsers, and this one in particular, is it's fairly easy to start and do a good coverage up to a certain point. Then the system becomes so complex and the intricacies of rules become so hard to follow that it's difficult to add past a certain level. To show you the kind of coverage it has, I just picked up randomly this morning paper here, and I just, on a section, I just take the first sentence, and we'll see what FIDIC can do with it. So this is an article by Pat McAdams called Memories of Joe, about Joe Clark. So the first sentence is, I first met the kid in 1959 when he was the national president of the Tory Students Federation. As you might have noticed, I've removed all capitals because FIDIC cannot deal with capitals except the pronoun I. So let's see what we get with this. So here is the trace. Let's take a look at the resulting parse. Okay, we have a sentence, noun phrase. The first was seen as an adverb, but was not attached. At least it's more interesting to have a parser that can tell you that it cannot attach a constituent rather than just attaching it somewhere randomly. Verb past, noun phrase. The kid. Okay, this PP was not attached. In 1959, it doesn't know about dates. Punctuation is unattached. Then you have an S bar. When he was the national president. Neither national or president are in the dictionary, but national was correctly identified as being an adjective and president as being a noun. Then president of, so the complement of the noun is indicated properly, even if the noun is not known. of the Tory Student Federation. So for a random sentence there, the parse is pretty good. In my own experience, we get approximately, for random sentences like taken from a newspaper, we might get 20% of acceptable parse, maybe another 30% of not far, and probably half of the parses that need serious fixing. The semantic representations used in Coda-X are based on Carl Friedrichsen semantic grammar. Propositional grammar, in fact. So it's a grammar that tries to define what a proposition can be. For instance, it can be a state or an event. If it's an event, it can have a possessive case frame or resultive case frame, which both have different slots. For instance, an object relation needs to have an object, which can be an object identifier or could be another proposition. The way the semantic parser operates is to first determine from the parse what are all the potential candidates for proposition. For instance, an adjective modifying a noun can result in a state proposition. Each verb could be a proposition of its own, and there are different structures that can proposition. So the parser is actually going to go through the semantic grammar and prologue style. It means following the different rules and backtracking for each case where there's a potential proposition, and then return the propositions. Two versions were done. The first one was hard-coded in Lisp. As an example, let's take the first sentence that we parse. I am parsing an easy sentence. So here is proposition. Okay. We can see it simplified notation only. Simplified notation in trees, or we can see the trace. Let's do a first pass only with the simplified notation. Start of proposition 1.1. Okay, what do we get there? We get a proposition which is unit 1, segment 1. The content is an event and the truth value is positive. This event has an act and a case frame. The act identifier is parse. The case frame has a patient, which is an object, which is made of a pronoun identifier. The object relation is an object, which is the determined object. The object identifier is sentence. The determiner is non-generic, and it's token singular. So this one is not bad. And then let's look. There's a second proposition. Okay, in that case, unit 1, segment 2, it's a state, positive truth value. It's an object, sentence, and an identifying relation, which is an attribute. An attribute identifier is easy. Now let's look at the same processing, but with a trace of the application of rules in the grammar. So now we see the parser trying to demonstrate that there's an event, looking for the object, object identifier, finding the determiner, and then getting the whole tree. Well, now it's trying to see if there's an instrument relation, and trying to see if there's an act relation, a recipient, looking for a goal, looking for a theme, then looking in the event for an identifying relation, looking for a part, a locative, a number. And it succeeds in the number relation, but fails on the following rule. Try to find an identifying relation, then looking for tense and aspect, looking for modality, then looking for truth value, then finds a positive truth value. Then that's the whole proposition. And let's look at proposition number 2. Looking for a state, finds an object, finds a determiner with a quantifier, looking for a second determiner, then looks for part relation, an attribute relation, finds an attribute identifier, easy, looking for a degree relation, like very easy, couldn't find any, looking for tense and aspect, for modality, for truth value. And here's the result. Let's try the same thing with a little bit more difficult sentence. First, let's parse the sentence. I went from the house to the store to buy fresh milk. Okay, we get the parse. The window is a little bit too small here, but I went from the house to the store to buy milk. It's not attached properly. Let's just reshape the window so we can see the whole parse. Let's reparse the sentence. We have a better view of it. So here it is again. So let's see what's wrong with that parse. I went from the house to the store, okay, to buy fresh milk. Let's try the fix for the adverbial phrase. To buy fresh milk was not properly attached, so there's a fix for adverb phrases. So it's going to be reattached at a proper spot. So let's try to fix everything. Okay, I went from the house to the store to buy milk. This is completely incorrect. So now let's see what's wrong with that sentence. I went from the house to the store. The PP is not attached properly, so I'm going to fix and attach the PP to the verb. Fix PP VP attachment. Okay. To buy fresh milk should be an adverbial phrase attached to the VP there. So let's try to fix that. I just realized that the fixing is done with the menu. It's not visible on the screen right now, but I just selected some of the fixes available down there. So this one looks okay now. I went from the house as a PP, to the store as a PP, and to buy fresh milk as a sentence used as an adverbial phrase. So now if I generate the proposition, I get the first proposition. Let's see what we get here. It's an event, the content is an act to go, and it's a resultive case frame. The resultive case frame has an agent, I, a source, which is the house, and a goal with basically two goals. One is a determined object, the store, and another one is a proposition. So the goal of the act of going is both an object, the store, and another proposition. So let's look what this proposition is about. It's an event. The act is buy. It's a possessive case frame. The object of buying is milk, and this whole proposition was seen as the goal of the first proposition, which is going. And there's a third proposition. So let's generate now and see what it is. It's a state that the object milk, which is universally quantified, as an attribute to be fresh. The milk is fresh. Also, as a result of this semantic interpretation, we get a simplified form of the proposition. In this case, we have three. First one, go, agent I, source house, goal store, goal 1.2, tense past, truth positive. So 1.2 is buy, patient empty, object milk, truth positive, and the third one, milk, attribute is fresh, truth is positive. The way this semantic interpreter works is by assigning patterns to be looked for inside the parse tree to each rule in the semantic grammar with some form of parameter passing. So in fact, each rule in the semantic grammar will actually test for some specific syntactic patterns and for some syntactic and semantic markers inside the syntactic tree. The problem with such an approach is that all those patterns were hard-coded in Lisp, so it was very hard for anybody else than me to actually modify and implement anything in the semantic engine. The thing is, many people in the team at the time could have helped to actually implement some specific rules. For instance, so we worked on the modality rules. So there was a need to create a simpler way to actually modify the semantic engine. So what I worked on after this was a rule-based programming language to fiddle and play with each semantic rule individually with a variety of tracing and monitoring tool to actually fine-tune those rules. At the first level, what was needed is a tool to create and edit the semantic grammar. Let's take a look at the rule. Let's take a look at the rule manager. Okay, there we can create a new rule, change the top level rule in the grammar, inspect the rules from other grammars. So all the rules that you see there on this big window are rules in the semantic grammar. For instance, let's take a look at the preposition rule. Okay, we can edit it here, create it here. So there are basically 9 rules here. Preposition can be an event, a system, a state, a conjoint dependency, etc. Let's look at the event rule. Edit the rule. So an event is just one rule, but a pretty long one. It's preposition number, an act slot, an optional resultive frame, an optional act identifying relation that can be repeated, optional tense, aspect, optional modality, and there's a truth value. For instance, if we look at what an act identifying relation can be, for instance, if we look at what an act slot can be, it can be either an act, or it can be empty, or it could be a WH question. Once a grammar is edited, the next step is to create what is called here calculators. In fact, what calculators are, they're basically patterns to look for to decide if we're going to have a preposition or not. In this case here, and what we only had 5 rules: possessive, an NP modified by an adjective, an NP modified by a PP, a simple question, or a sentence. So let's look at NP modified by adjective. If anywhere in the tree you have the following case, an NP, which is then assigned to variable u, that dominates a nominal phrase, that dominates an adjective, which is assigned to variable v, then a call to proposition will be made as parameter 1 is going to be the NP, parameter 2 is going to be the adjective, and parameter 3, which is a type, is going to be called adjective. Each of those things could be modified for other variable, or the type could be modified here. Each calculator can be then compiled and can receive some documentation. Then each rule in the semantic grammar will have associated with it a series of what is called here dynamic rules. Let's focus a little bit on this. Okay, in the case of the event rule, we have 9. Those are the actual rules that will trigger or not the application of that rule. For instance, some here are called model as bar verb. Let's look at what this rule looks like. Okay, so the actual work of defining the semantic interpreter is to create and test those rules. They're actually made of 5 or 6 parts. First is a pattern. Here, for the rule to be triggered, you must have, in that case, a match on the first parameters. You must have a tree with an S, NP, VP, anything under the VP, and the first left element under the VP being assigned to variable V, and then the whole subtree under the S bar being assigned to U. Then there are a series of tests, and that for that rule to work, the element V must be in the set of modals. Somewhere else, you can edit a variety of sets, then you can test if some lexical elements are part of that test. Other possible actions are to test for semantic marker, for syntactic marker, to test if this element governs another one, if it's equal to a certain value. And then you might take some actions. In that case, there's an action called forget proposition, was probably because in that case there was a proposition calculated because of the sentence under the S there, the S under the S bar. The action is to forget that there was a proposition there because this rule found a better application for that S. Other possibilities is just to have straight Lisp, but it could be change, delete the subtree, move the subtree, create a new proposition that could not have been found by the calculators originally. And then there are a series of calls to the sub-rules. In that case, for event, we already saw that there were 6 or 7 sub-rules there. So the prop number will be called with parameter 4 that would pass to this rule. The act slot will be sent to U, which is a subtree under the S bar. Same thing for the resultive frame. The modality rule is going to be sent the original sentence as a whole. To see how those rule work, let's do an example. Let's use the sentence, the original, the first sentence we try. I'm parsing an easy sentence. Now let's select generate proposition. Let's go with simplified notation and trees. Start of proposition 1. In this case, we got an empty tree. Let's look at proposition 2, and we also get an empty tree. This is because in that version of the program very few rules have been actually specified, but we can look at what happened during that generation. So I select trace/generation, trace everything, And I want to see what happened in proposition 1.1. Then this is the trace. Let's try to zoom in to see a little bit more what this is about. So the rules for event were applied, but they all failed. The first few ones, the pattern failed, and the last one, the action failed. Then the rule for system was called, the pattern failed, the rule for state was called, and then the second rule for state was successful. You went into state object, into determined object, and eventually the test failed on determiner. Then all other version of object failed, and so in fact we would like to, when we do the tracing on such a parse, we first need to determine which rule should have succeeded. In that case, the sentence was, I'm parsing an easy sentence, it should be an event, and probably because there's a semantic marker on parse. So let's see the result from application of that particular rule. And that's what we get here. Tracing, pattern, fail, even, verb, semantic marker. Input parameters. P1 was NP, an easy sentence. So in fact, as I realize here, the first parameter of pass is actually the NP, so this should have been a state. So let's look at which rule we would have liked to succeed in that case. It's probably state, adjective modifying a noun. That's the one, but this one succeeded. Let's look at a successful rule and we'll see what went wrong after. Okay, so we have the parameters, result of pattern matching. P1 had to be matched with NP, nominal adjective. Pattern matching succeeded. So let's see what went wrong. The problem here is that the state object rule actually never succeeded. So let's just see what the rule is asking for. It's simply a match on an NP, and then it passes the rule down to object. In fact, the problem can be easily traced here because state object is an object, determined object. In our case, the determined object is an easy sentence. It could not find a determiner. All determiner rules eventually failed. It should have been a non-generic determiner, but the test failed in non-generic determiner. So our problem is actually the non-generic determiner rule. So let's look at that rule and let's try to see why the test failed. What it does, it takes an NP, look for determiner under the NP, and eventually assign the specific determiner to variable u. So there's a test after that u as a semantic marker, non-generic. So the problem is probably that the word "an" in our lexicon doesn't have that semantic marker. If we go back to our parse, we can check for that. Let's look at "an." Yeah, and it has no semantic marker. So let's look. It's non-generic. And let's save the result. And let's retry our semantic generation. So now, after we changed our lexical element there, let's try proposition 1, which is the one we're looking for. And we still have an empty tree. Let's try to find out why. So this is our new trace window. Event fail, that's okay. So state, adjective modifying a noun, object, determined object. Now non-generic actually succeeded. Non-generic determiner the fail, non-generic determiner an actually succeeded. Then we have non-generic quantifier, blah blah blah. Then the whole state object did succeed. Then the place where we actually failed is in state identifying a relation. Most of them are empty rules. So in fact, the rules that looks for a relation, in that case an attribute relation, is easy, was never written. There's one rule, pass arg of VP to attribute. We can look if this one is the one we're interested in. See result from application of rule. And this one was trying to match an NP with an S. So this is probably not the rule. This is a different rule that doesn't apply to our case. We have another tool here where we can directly see compare the pattern that was sent to the rule, the parameters that was sent to the rule in the actual pattern. In this case, we can see the pattern was SVP, and the original was NP, determiner noun, so it could not have matched. So the solution here would be to actually write the rule that is necessary. A variety of tools also were added to simplify working with this program. The tracing, we looked at it a little bit. The editors, there's an editor for syntactic marker, the semantic markers, different sets that can be created for testing if a particular lexical element is part of a set, for instance. Rule manager, where we can import and export rules between grammars. Probably the most complex tool is called Coda-X scope, and it can basically do three things. It can show all rules that are never called, and the rules that can be unreachable. There's also another application of Coda-X scope. For instance, if I select a particular rule, like non-generic determiner, I can turn the trace on or off, rename the rule, delete the rule, but I have specific Coda-X scope options. I can see the bottom-up calling scope. Let's see it at small level. This tells us that non-generic determiners calls non-generic, which calls a determiner. But we can see it also the top-down calling scope. A non-generic determiner can call a token or a definite. This scope can be increased or reduced, so we can see exactly how the grammar is constructed at the specific level. Okay. Another interesting option is to immediate parameter passing, is to see what are the types of parameters that are passed immediately, but a more complex tool is called parameter passing analysis. In this case, the program will look towards inside the whole grammar to see what are the type of okay, let's cut on this. For a specific rule, Coda-X scope can offer a variety of tools to understand how the grammar is built and how the rule calling is going to proceed. We can see the rule calling hierarchy either from bottom up or top down. For instance, I selected the rule determine object. Determine object here will call object, which can call any of those rules directly. Let's close this. Let's look at determine object. Next scope. Let's look at the top-down calling scope. So determine object will call determiner or prop number determiner. So we see it at 3 level. We could see it at a higher number of levels. But the more complex aspects of Coda-X scope is the capacity to analyze the way parameters are passed, because there are no typing of parameters, so any rules can pass any parameters to any other rule. But by looking at which rules have been written, there's a way to determine what are the types of parameters that those rules can eventually receive. So this parameter passing analysis here gives us the following cases. So the rule determine object could receive an S from concept, from recipients, or from result. Most of the time we'll receive an NP from those different rules. If we look at each of them individually, for instance, we know that the parameter 1 can be an MP from agent relation. Then that would be passed to agent, and passed to object, and passed to determine object. This is extremely useful because it allows the person who writes the rule to know exactly the type of trees that will be received by that rules, and can treat the different cases. It is unfortunate that nobody besides me actually had time to program rules or to play with the system. Right after this thing was functional, funding for this project was kind of cut, and eventually those machines became obsolete, and we passed to something else. This is the last survivor of 3 machines. One is completely gone. Another one has a serious software problem. It probably needs a reinstallation with some diskettes that are not very reliable. This one behind me might go very soon. So this whole program is now only on this hard drive and on some diskette formatted with a very strange format called Pilot. So eventually my goal is to try to get the content, the source code on some other more respectable machine, and to try to have at least the parser that's part of it run on the Mac or PC.